Okay, welcome to lecture. Hopefully everybody's here. It looks like, yeah. So we're going to continue on in lecture just a little bit here. As we talked about, we're going to stop around 8:30, and you could go take your quiz that's going to happen today, again on Canvas like we usually do. So we've been talking about acid and bases regarded to sort of pH, pOH, and some of those things. So again, a reminder that Kw equals the H plus concentration times the OH minus concentration, and that equals 1 times 10 to the minus 14. And again, we can use that to calculate either the H plus or the OH minus concentration, and we can compare those two and determine if it's acidic, basic, or neutral. So if the H plus is larger than the OH minus, that's going to be an acidic solution. If the H plus is equal to the OH minus, it will be a neutral solution. If the H plus concentration is less than the OH minus concentration, it will be basic. We also talked about the pH scale. So the pH scale is minus the log of the H plus is how you calculate it. And it goes from 0 to 7 to 14, less than 7 being acidic, above 7 being basic, and again on 7 there being neutral. Remember that when you do calculate the pH, if you do have a display calculator, you want to go with the negative button, the log, and the number using scientific notation and your exponent button. Um, if you have a non-display calculator, again, this one and the others, you need to go backwards, start with the number, hit log, and then hit the negative. As you go from 7, again, closer to 0, that's more acidic. As you go from 7 to 14, more basic. And again here, the pH scale is typically what we use to determine if something is acidic, basic, or neutral. Um, on that very last example, some of you miscalculated the pH, and what you actually calculated, we talked about at the very end, what was known as the pOH, and that is minus the log of the OH minus concentration. And the pOH runs opposite of the pH scale. So the pOH scale, if you want to think about it that way, again, it runs opposite. So we have 7, 14, and 0. So actually below 7 is basic on the pOH scale, above 7 is acidic. So it's opposite. And that's why when I talk about determining acidic, basic, or neutral, it's always the pH scale that you want to look at, because that's pretty much what everybody has in their head. Most people don't have this one in their head. So make sure that when you are asked a question like that, is it acidic, basic, or neutral? As we talked about last time, there is really only one answer to that, is either acidic, basic, or neutral. And you should always look at the pH value to determine that, again, because pretty much that's the scale that most people have in their head. But the nice thing that we saw at the very end there was that the pH plus the pOH will equal 14. So it does give you a little bit of variety in terms of how you can answer some of these questions. If you're just given the OH minus concentration, you could calculate the pOH, and then you could subtract 14 and get to the pH pretty easily. So it is sort of beneficial in that sense. Any questions on any of that stuff we were talking about last time? Again, if you do have questions, feel free to ask them in the box there. That's a good shot. I should have wrote all over that, I suppose. Huh? Let me get rid of all that stuff I put on the screen. There you go. So when we talk about the pH scale, again, it is based off of sort of the log of 10. So basically for every pH that you change, so if you go from a pH of 3 to a pH of 4 to a pH of 5, you're changing the H plus concentration by basically a power of 10. It goes from 1 times 10 to the minus 3, 1 times 10 to the minus 4, and 1 times 10 to the minus 5. And so every time you sort of change a pH unit, you're really changing the H plus concentration by that power. of 10. And as we talked about, a couple important relationships that we see as the H plus concentration increases, the pH goes down, and vice versa. Obviously, as H plus concentration decreases, the pH will go up. And that really is also tied to what we saw with the KW, that the H plus concentration, if it goes up, the OH minus concentration goes down, and also vice versa on that one as well. OH minus would go up. So they basically run opposite of each other. So as one goes up, the other goes down. So in the case of H plus, if it increases, that means that the amount of OH minus, which is kind of like the basic part of the solution, gets smaller, and thus it is more acidic, and vice versa. If the H plus concentration went down, the OH minus concentration would go up, which means the basic part of the solution would be larger, and the pH would also go up as well. Now, there's a couple different ways you could measure pH, for example, and these are two sort of common ways that you could do that. One is by using a pH meter, and pH meter is what we see on the left here. It's basically an electrode and does a little chemical reaction, but essentially what it measures in a beaker or solution is the amount, and remember what affects pH is the amount of free floating H plus ions, right? So it's able to measure basically the amount of free floating H plus ions in the solution and give you a digital reading in most cases, like you see there, what the pH would be. Now, there's also color indicator paper, or sometimes it's referred to as pH paper. And pH paper, like you see on the right there, you essentially dip into the solution and it kind of changes colors. And, there's a little key usually on the box, as you can see also in the picture. And you pretty much try to match up the colors and go, it kind of looks like this set of colors. And, that means it's a pH of 2. Obviously not as accurate as, say, a pH meter, which gives you, as you can see in the example there, like 3 decimal places. But it's another way. Kind of similar if you have a pool. If you ever measured pool type chemicals, you take the little papers, you dip it into the pool, and it kind of changes the color. You try to match up all the colors. It's kind of a similar idea. Now, we also use litmus paper, and it really doesn't measure pH or tell you the pH of the solution, but we do use litmus paper to figure out if something is acidic or basic. And again, not going to give you a pH value here, but if you have blue litmus paper and it goes to red, it means it's acidic. If you have red litmus paper and it goes to blue, it means it's basic. So again, not going to give you a pH value or anything like that, but very commonly used with acid and bases is litmus paper, just to determine whether or not the solution overall is acidic or basic. So here's our pH scale. Again, we can see up on top here, we have something like sodium hydroxide, which is a strong base. So it's obviously basic. On the other end of the spectrum here, we have hydrochloric acid, which is a strong acid, so it's acidic. We have some vinegar, which is acetic acid, lemon juice, and all those kind of guys are obviously acids. Household cleaners, ammonia, which are typically basic type items. We have pure water here at 7. By the way, if you take water and you measure the pH, sometimes people are surprised of the pH of water, especially if this water is not really filtered very well. It's been sitting out a while. Actually, a lot of times water will be acidic, like a pH of 5-ish times, it can even drop down to. And that's because as water, for example, sits outside in the open air, picks up a little CO2 plus some water, and it makes something like carbonic acid. Carbonic acid increases the H plus concentration a little bit and drops the pH down from, say, where we maybe think water would be at 7. But if you have pure water, or if you take water and you boil it, it'll get rid of the CO2 and it'll bring the water back up to like a pH of 7. But sometimes people are surprised when they kind of put the pH meter into some water. Again, if especially it's been out for a while, kind of outside exposed to air and all that, that it's actually not 7. It's actually a little bit acidic and stuff like that. So we sort of got to this a little bit earlier here, but again, a similar scale to pH is pOH. And again, these names basically tell you what you need to calculate it. pH means you need the H plus concentration. pOH means you need the OH minus concentration. And again, as we talked about, when you're trying to determine acidic, basic, or neutral, always look at the pH scale. And again, that important relationship that the pH plus the pOH equals 14, again, allows you to do some calculations relatively on the quicker side based on the information that's given to you. So again, these are our important equations here so far. I'll add our KW there into the mix, as we saw earlier. Now, there is a couple other sort of equations that are important as well. So let's talk about those. If you are given the pH, from that information, you could actually get the H plus concentration. And if you're given the pH value, you want to calculate the H plus concentration, what you do is you take the inverse log of the minus pH. Now, most people's calculators, when you hit the inverse log, it will pop up a 10 and a caret and make sure it's negative pH. And you could also calculate the pOH from the pOH value, the same deal. You could actually get the OH minus concentration directly from that. And it's the same calculation, the inverse log of the minus pOH. Again, usually A10 and a caret minus pOH. So on most people's calculators, up there in the top left corner, there's like a second button, like a shift button. And on most people's calculators, obviously you have the log button, and usually there's a 10 to the X or something like that above it. So that's what inverse log is. You hit the shift, you hit the inverse, then the log. And then again, on most people's kind of calculators, it will display that 10 and the caret. And again, that's how you do inverse log. Some calculators have a dedicated button for that, but most you have to hit kind of the second or shift button along with the log button to get to that 10. And again, you want to also make sure you use your negative button. Not your subtract button to make it negative, and then pH or pOH. So these two are also important little sort of equations or formulas, again, allowing you to get right to the H plus concentration or the OH minus concentration if you have the right information, and allowing you to, again, perhaps not having to even use KW in a calculation. Any questions on any of those there? And with those formulas too, just like the calculators before, if you have a display calculator, you would put it in exactly like that. You would hit the inverse log button and then hit the negative button, then type in the pH. If you have a non-display calculator, you also have to go backwards in this equation as well, which means that you should start with the number, then make it negative, and then do the inverse log button. So like normal display calculator, type it all in just the way the formulas are written. Non-display calculators, you need to go backwards in most of these sort of formulas. All right, so let's try some here. So why don't you take a minute or so here, and we want to calculate the pH and the pOH for each of these solutions and see what you come up with, and then also decide, is it acidic, basic, or neutral? So take a minute or two, and then we will talk about it. Okay, let's take a look here and see how we're doing. So, excuse me, in the first one here, we have the H plus concentration given to us. So again, because we have the H plus concentration given to us, that's going to allow us to go directly into our pH equation. So we'll take minus the log of 3.6 times 10 to the minus 9. And if we do that there and put in those values, again, making sure to use your exponent button, looks like we get something like 8.44 as our pH. To get our POH, which it also asks for, that is going to then be 14 minus the pH. And that means 14 minus 8.44 is going to give us a POH of 556. Now, a couple of things, as we also talked about last time, in terms of how far to take our pH and POH reading, it is based off of our concentration. That's two significant figures. Again, gives me not two significant figures, but two decimal places. Same thing over here, that we would have our two decimal places as well. So remember that the concentration, the number of significant figures in the concentration will tell us how many decimal places we should take it to. Now, when we look at this to determine if it's acidic, basic, or neutral, we do want to look again at the pH value. And we see that the pH value is above 7, which means this guy here is going to be basic. Any questions on any of those calculations there on that first one? All right, looking at the second one, we are given the OH minus concentration. So because of it's the OH minus concentration, we cannot directly calculate the pH, but we can calculate the POH, which is minus the log of the OH minus. And we can put that into there, and that'll give us 9.2 times 10 to the minus 2. And that's going to get us 1.04 as our POH. Again, two significant figures, two decimal places in terms of the answer. And if we subtract 14 from that, that's going to give us a pH of, again, our pH would equal 14 minus 1.04. Looks like a 12. What we got there? 96. Yep. 1296. Now, again, when determining our acidic, basic, or neutral, it is only one of those answers. And here again, we're going to look not at the POH, but we're going to look at the pH value. And we see it again, it's above 7. So this guy would be basic. Any questions on either of those calculations? So again, very, very common. People will look at both of those numbers and give two different answers in terms of acidic, basic, or neutral. Again, they'll look at the first number and go, oh, it's above 7, so it's basic. But then they'll look at the second number and go, oh, wait, it's below 7, it's acidic as well. So again, just one in terms of those answers, acidic, basic, or neutral. All right. So here, the pH of the solution is 5.56. What is the POH? So again, to calculate this, we can use that relationship that we saw. You don't have much of a calculation here. Again, that the pH plus the POH is going to be 14, which means in this case here, the POH would be 14 minus the pH that was given to us. And that would get us 8.33 as our POH. And in this case, again, if we were wanting to determine if it's acidic, basic, or neutral, we would actually, again, look at pH number, which is 5.67. And that is less than 7, which means it is acidic. Let's see. So, do you always subtract 14? You do, I won't say always, but you do if you have, for example, this relationship here. And what I mean by that is either you have the pH value or you have the POH value and you want to find the other. So that's where we would subtract 14. And it is always 14 the number when you're using that relationship. And it's really based off of the pH scale is, goes to 14. But we use the 14 minus either the pH or the POH. Again, if you have specifically one of those values and you want to find the other. So that's basically why we use the 14. Other questions on that? And again, it is specific for when you have either the pH value or you can calculate the pH value, or if you have the POH value or you can calculate the POH value. And again, want the other. Other questions on any of that? All right, so why don't you give this a go? Make sure your calculator works and all that good stuff. Here we have the pH of a solution is 3.14. What is the H plus concentration? So take a minute or so here and give it a calculation, see what you come up with. Okay, so again, in this case, we have the pH given to us, and we're looking to find the H plus concentration. And we could do that if we know the pH. Again, to get us to the H plus concentration, this is the one where we do the inverse log of the minus pH. Again, that's a 10 and a caret on most people's calculators when you hit that in. So if you do that, the H plus concentration in this case would be the inverse log of the minus 3.14, which again, on most people's calculators would sort of look like this, perhaps. And if you do that, you will end up with something like 7.2 times 10 to the minus 4. Since this is a concentration, you would put molarity there. And a couple of things about that answer, your calculator may not give it to you in scientific notation, so you may have 0.00072 given to you, which is fine as well. But we're going sort of the other way here in terms of from pH back to concentration. So when we do that, we also want to think about sort of those sig figs. And if we look at our pH value, we had 2 decimal places, which gives us 2 significant figures here when we go backwards. So again, if you go sort of backwards from pH to the concentration or the concentration back, you do want to kind of watch those sig figs. This solution as well would be acidic as it is 3.14, which is less than 7, and that's the pH value. And that's how we would know it's acidic. Any questions on that calculation? Okay. So why don't you try it here with this one? This is the POH value of 5.67. What is the OH minus concentration? Okay, so here again, we're going to basically do the same thing. Remember that if you are given the pOH, from the pOH, you can get the OH minus concentration. And it really is the same calculation for all this stuff. It is going to be the inverse log of the minus pOH. So in this case, the OH minus concentration would equal the inverse log of the minus 5.67, which again on your calculator will probably make it look something like this. And if you do that, you will end up with 2.1 times 10 to the minus 6. Again, we would put the molarity there as a concentration. And same idea here. We had two decimal places, going to give us two significant figures when we go into our concentration. Again, here, may not give it to you in scientific notation, your calculator, but a lot of times people will put these into scientific notation, but you don't necessarily have to. More importantly, get the right number of sig figs, but probably a scientific notation would be good. So a reminder, again, if you were going to punch this in sort of into your calculator, on most people's calculators, to get to the inverse log, top left corner, you usually have a second button or a shift button. You would then hit the log button, which usually has like the 10 and the X or something above it. And again, if you have a display calculator, when you do that, it'll probably put up a 10 and maybe a caret. Then you want to hit your negative button, which looks like something like this. Again, not your subtract button. And I'll put the negative, and then obviously just type it in the number 5.67, 5.67. So if you have a display calculator, that's basically how you would punch it in. If you have a non-display calculator, it's basically the same deal. You're just going to go backwards. So you would start with the 5.67. You then would hit your negative button. You then would hit your second button or your shift, and then you would hit your log button. Yeah. So again, depending on the type of calculator you have, you would go both of those ways there. Yeah. So again, if you remember when we were talking about sort of sig figs and pH, when we go from concentration to something like pH or pOH, it is the sig figs to how many decimal places in each of these numbers. So again, it's concentration had two significant figures. That would give you two decimal places. So we're basically doing the opposite of that calculation. We got the pH or the pOH, and we're going back to concentration. So basically what we do is just the opposite of that. If we have decimal places here, that will tell us how many significant figures we should have in our concentration. So kind of works the same way. It's just, we're kind of going opposite in this case. So here, when you go from pH or pOH to concentration, you're going from decimal places to how many sig figs that should be. And you're doing the opposite when you go from concentration to pH. It's sig figs to decimal places. Yeah. Any questions on that there? Other questions I could help you with on this one? And again, like I said before, when you do put those into your calculators, sometimes in a lot of cases, if your calculator is not set to scientific notation, again, it will not necessarily give it to you in scientific notation or anything like that. All right, so what happens when we do have a strong acid or something like that? And up until this point, we've been calculating the pH, the pOH, and all those things kind of from generic sort of things. So, they generically say, hey, the H plus concentration is this, or the OH minus concentration is this. But what do we do if we're actually given a formula of an acid, and especially a strong acid here? How do we calculate the pH or pOH for a solution like that? So, a couple of things that we will know is, as we talked about in this chapter, a strong acid or strong base is a strong electrolyte, which means it will 100% break apart into ions. And that means that when we want to calculate something like the pH in this case, it is the H plus concentration that's important, which means because this thing 100% breaks apart into these ions, we can figure out the H plus concentration relatively easy. So if we had a zero point 0.1 molar solution of HCl, what that means is that HCl will break apart into H plus and Cl minus. And if the whole thing is zero point 0.1 molar, we could figure out the concentration of each of these ions by kind of using like stoichiometry, if you will. It's basically a 1-to-1 relationship between the whole thing and the H plus, which means if we want the concentration of the H plus, it would also be 0 0.1 molar. For the Cl minus, it's also a 1-to-1 relationship, which means its concentration would also be 0.1. Although in this particular case, we don't really need it because we're really just interested in the H plus concentration. So once we figure out the H plus concentration, the pH equals minus the log of 0.1 in this case. And that would get us a pH of, if I hit the right number there, a pH of 1.00, right, which is definitely acidic and would definitely be good because this is a strong acid. So sometimes you'll be given the formula of a acid or base, and for our purposes in this class, what that essentially will mean is it's going to be a strong acid or base. Weak acids and weak bases require a little bit longer of a calculation, which we don't get into here. If you go and eventually take 1B, you'll get into those calculations. But for us, if you see a formula of an acid or base, especially on a quiz or an exam, you could probably safely assume that it is a strong acid or base, and it will 100% break apart. Again, a reminder, HCl, H2SO4, HClO4, HBr, HI, HNO3. These are all strong acids that we come across. A lot of the strong bases like sodium hydroxide, potassium hydroxide, again, they have that OH minus in it as part of the formula. So again, for example, here, if we are given this is perchloric acid and is 0.025, we would break it apart because again, it is a strong acid. So it would 100% break apart into H plus and ClO4 minus, which is perchlorate. And we would find the concentration of our H plus here by doing that relationship. It's a 1-to-1 relationship, which means the concentration here would be 0.025. And again, we don't really have to worry about this in terms of pH. So the pH here would be minus the log of 0.025. And that would get us a pH of 1.60, which again is acidic, which is good because this is an acid. So we would expect that. Any questions on that? So why don't you try one here? Why don't you try what you think the pH of a 0.025 molar calcium hydroxide solution would be. And for our sake of this example, we'll say this is a strong base. So take a minute or so and see what you come up with. Okay, so when we look at this one and we want the pH, we need to look at this. And first thing we should see is obviously we're going to assume this is a strong base. So when this breaks apart, it is going to break apart into a calcium ion, but it's also going to break apart into two hydroxide ions when it breaks apart. And in this case, although we don't have the H plus concentration, we can get the OH minus concentration. And that's going to be good because that will get us to the POH. And from the POH, we could then get to the pH of the solution. So when we look at the whole thing, which is 0.025 molar, it's a 1 to 2 relationship here between that and the hydroxide, which means to find the concentration of the hydroxide, we actually need to multiply it by 2. And that will get us 0.05 molar as the concentration of hydroxide. So it's important when you do these things, sometimes they don't necessarily break apart always into a 1-to-1 relationship. Maybe a 1-to-2 relationship like here where you need to multiply by 2. Could be a 1-to-3 relationship you need to multiply by 3. So that's going to give us our OH minus, which means our minus the log of 0.05 will give us our POH of 1.30. And again, a reminder that this is not the pH, this is our POH. So because we are starting with a base here, we're going to have to use the pH is going to be that 14 minus the POH. And that would get us 14 minus 1.30. And that's going to give you 12.70. Whoops, come on back. There we go. 12.70 as our pH value. And that does make sense when we think about this. If we consider this a strong base, that means that the pH value there is above 7 and we are basic. So that again would make a lot of sense here in terms of what we're looking at. So when you are given a formula, again, for our class, you could assume pretty safely that it's a strong acid or base. Again, weak acids and weak bases are a much more complicated calculation that we don't get into here. But again, if you take 1B or something like that, you will definitely get into those. Any questions on that? Okay, so the last thing here we're going to talk about in this chapter are buffered solutions and a buffer. And a buffer is a solution that is able to resist changes in pH, even if you add acid or base to it. So a couple things about a buffer solution. Sometimes people think a buffer is a neutral solution, and that's not always the case. It could have a buffer that's neutral. You could also have a buffer that's acidic. You could also have a buffer that is basic. You basically could make a buffer for any pH you like. What a buffer means is, for example, let's say we made a buffer that had a pH of 5. If we made this buffer and had a pH of 5 and we added some acid to it, what we would expect to happen is the pH of that buffer solution would still remain around 5. It might go down a little bit, maybe 4.9, something like that, but it will still be in the pH of 5 neighborhood. We wouldn't add acid to the buffer and expect the pH to go from 5 all the way down to like 1 or something like that. And same thing, if we take this buffer and we add a base to it, like sodium hydroxide, we would expect the pH again to remain around 5. In reality, it'll go up a little bit, maybe 5.1, something like that. But we wouldn't expect the pH to jump drastically, say from 5 to a pH of 12 or something like that when we add a base to it. And the reason a buffer is able to maintain its pH is because of what it's made up of. So a buffer is made up of either a weak acid and its conjugate base, or sometimes it's referred to as the salt of its conjugate base, or it's made up of a weak base and the salt of its conjugate acid. And the important part here is the weak part of it. You cannot have a buffer that is a strong acid or a strong base. And that's because if you have a strong acid or base, it 100% breaks apart into ions. But if you have a weak acid, for example, something like acetic acid, which is a weak acid, when it goes for a swim there in water, it breaks apart into acetate and H plus. And it sets up this reversible equilibrium reaction. And it's a weak electrolyte, which means we mainly have a lot of this guy there and we have some of this guy there. So in solution, we have the weak acid and its conjugate base. And that's different than if you put it in something like HCl and try to make a hydrochloric acid, try to make a buffer out of that. What you're going to only have in that solution is these guys. And that means you'll only have a conjugate base. You'll have no acid part. And that's important for how a buffer is able to function, because really a buffer, if you think about it, I'll draw a nice little picture here. Inside the buffer solution, you basically have an acid part, like acetic acid. And you also have a base part, like sodium acetate. So acid part and base part. And that both of those guys are in a buffer to begin with, and that's why it's able to function well to maintain the pH. So let's talk about exactly how it's able to do that and how things that are not buffers are not able to do that. So for example, if we take water, which is not a buffer, and to water, if we add some hydrochloric acid, when it goes into water, it's going to be 100% H plus and Cl minus. And what we have done is, again, 100%, as we talked about, will be these guys. We have just produced a lot of free H plus really quickly. And if you remember, the pH is minus the log of the H plus concentration. As the concentration of H plus increases, the pH goes down. So in this case, again, if the pH of water, say, was 7 and a nice neutral water there, if we add some HCl to it, it would go from like a pH of 7. And again, I'm just making these numbers up. Say it started at a pH of 7. Maybe it goes down to like a pH of 1, a pretty big jump in the pH, again, because we made a lot of H plus very, very quickly. If we take something like sodium hydroxide and add it to water, which is a strong base, it also 100% is going to break apart into sodium ions and hydroxide ions. And although we don't have a lot of H plus being made, we did make a lot of free OH minus. And that's important because as the OH minus concentration increases, that means the H plus concentration is going to decrease. And as the H plus concentration goes down, the pH will go up. And so since we made a lot of those free OH minuses, again, we'll just assume the pH started at 7. It maybe will jump to a pH of 12 or something like that. Again, a very big jump in pH. And that's because in water, which is not a buffer, when you add those strong acid or bases to it, you generate a lot of free H plus in the case of the acid and a lot of free OH minus in the case of the base, all of which has a pretty drastic effect on the pH of the solution. But now if we take those same things and we add it to a buffer, so we'll use our acetic acid and we'll use sodium acetate, which again is really just a source of acetate. Okay, so the acetic acid is the acid part of the buffer. The sodium acetate is the base part of the buffer. So when we add our HCl, like we did above, to the buffer, the HCl, which is an acid, is going to react with the base part of the buffer. And we'll get some sodium acetate in there. And what's going to happen in this case is really a double displacement. You're going to get some acetic acid that gets made. and you will get some sodium chloride. So basically a double displacement reaction occurring here. These two guys are going to switch partners. And importantly, when we look on the product side, we made some acetic acid, which is part of the buffer to begin with. So that's not going to mess up the pH. We also made sodium chloride, which is neutral. It's a neutral salt. Again, because it comes from a strong acid and a strong base, and it will not basically do anything to the pH. But more importantly, what we do not see on the product side here that we do see up here is this. We do not see any free H plus formed. So since we didn't make any more H plus, the H plus concentration remains relatively constant. And because the H plus concentration is relatively constant, the pH remains relatively constant as well, because we didn't get a big jump in the amount of H plus that's being made. Now, if we take sodium hydroxide like we did above and we add it to the buffer, it's going to react with the acid part of the buffer, acetic acid, and it's going to do an acid-base reaction, and it's going to make sodium acetate and sodium acetate there and some water. Just like we see above, what we do see is we actually made the buffer part as part of the products. But just like above, we do not see an important thing showing up. We do not see OH minus. So we made no more free OH minus. And that means that our H plus concentration, because they are tied together, will remain relatively constant. And because the H plus concentration and the OH minus concentration is relatively constant, the pH itself will also remain relatively constant. So I say relatively constant because, as I talked about, you will actually see a slight jump up or down in the pH when you add an acid or base to it. But again, here, for example, if our pH started at, say, 4.74 and you added the acid, maybe it goes to like 4.65 or something like that. A very small change in pH, not a drastic change like we would see above. And same thing here, if you added, say, you started at a 4.74, which is about where this would start. Maybe it goes to 4.8 or something like that. But you won't see a very drastic jump in the pH. And the reason for that is really a buffer. What it's able to do is prevent the formation of free H plus when you add acid, and prevent the formation of free OH minus when you add a base to the buffer. And ultimately what that does is it allows the H plus concentration to remain relatively constant. And that means that the H plus concentration will be relatively constant, and so will the pH. Any questions on how a buffer works? So just to kind of graphically show you here, very bad drawing here. If this is our buffer, again, there's an acid part and a base part to the buffer. And again, both of those things are in there to begin with. When you add acid to that buffer, it's going to use up some of the base part, and you're going to make some of the acid part of the buffer. So the acid part of the buffer will increase. The base part will get used up a little bit. Same thing if you take that buffer and you add base to it. It will use up some of the acid part of the buffer, and you'll make more of the base part of the buffer. As we saw there, you make more of one part of the buffer while you use up the other. And again, here, the acid part will get smaller. And that's important because this shows that there is a limit to buffer capacity, is sometimes called. So for example, if you think about over here, if you just keep adding and adding and adding more acid, or if you add too strong of an acid. Eventually what's going to happen is the base part of your buffer is going to get smaller and smaller and smaller until at some point it's no longer going to really be there effectively. And at that point, your buffer will stop working and you will see a big jump in pH. And same thing here as well. If you continue to add more and more base, you're just going to chew up the acid part of the buffer. And again, at some point, you could actually blow through the buffer and it wouldn't be effective in maintaining the pH. But usually a buffer is pretty effective if it's at the right concentration and what you're adding in terms of acid and base is at the right concentration. It's able to work over a long period of time. So a buffer has to contain a weak acid and its conjugate base, or a weak base and its conjugate acid. And again, basically by reacting with acid or base that's added to the buffer, it prevents that formation of H plus or the formation of OH minus being there freely in the solution, and thus being able to maintain the pH relatively constant. Any questions on how a buffer works? Okay, so I believe that is it for this chapter. So that is chapter 9. So we have next week, the 28th, is going to be our final, right? And not our final, I'm sorry. Next week is going to be our last exam on the 28th. And then I think maybe the following week or so is our final, or we're getting close to the final, I think. So it'll be like the following week, I think. It will be changed, so I'll change it. The homework will be changed, so it'll be due at the end of next week. So next Wednesday is the last exam that we're going to take. It covers through this chapter, and then I think it's a good question because it is the holiday. I'm trying to think whatever it says on the schedule. I don't remember if the holiday or not. I'll double check and I'll let you know if we will have one or not. Been a long time since I looked at the schedule there in terms of that. But I'll let you know if we do. The final is cumulative. I'll double check on Monday. We will. So we'll start lecturing on that. If not, we'll have some type of recorded lecture for some of those if we needed to. So you can at least watch those, if not live. All right. Any other questions? So went a little bit long here, but your quiz should be available at this point. So go make sure you go take the quiz, and then I'll double check on Monday and stuff like that. So the next exam will cover, I want to say, I think it's 7, 8, 9. I double check whatever it says on the syllabus, but I think 7, 8, 9 sounds about right if I'm not mistaken. So I think it should cover those. Yeah, the quiz should be in the quiz module. It should be open. I think it opened at 8:30, so it all should be open and ready to go. So you could go take that and all that kind of stuff. And again, I'll double check on them on Monday and stuff like that if it's the holidays. I don't remember if we had class or not. So if we don't, then maybe we'll do probably a recorded lecture or something like that, just to kind of keep us on pace and stuff. All right. Other than that, have a good weekend and all that good stuff. But do make sure you go take your quiz, okay? Thank you, guys. Have a good day.